Complexity classes. In this section, we will encounter some of the most intriguing problems of modern mathematics. They are related to attempts of describing which questions can be decided by Turing machines in an efficient way. The class P, a decision problem, is a yes or no question asked about a combinatorial object, such as is this graph bipartite, or is this graph connected, or is this integer prime, or does this permutation contain an even number of cycles of length 7. A language L is the set of all objects for which the answer of a given decision problem is yes. So, following up on the above examples, the class of all bipartite graphs, the class of all connected graphs, the set of all prime numbers, and the set of all permutations with an even number cycles of length 7 each form a language. We will say that a Turing machine T accepts the language L if given input X, T stops in the accepting state if X is in L, and T stops in the rejecting state if X is not in L. We are now ready for the first major definition of this section. Definition 18.2. We say that a language L is in P if there exists a Turing machine T and a positive integer k, so that T accepts L in big O of n to the k time, where n is the size of the input. That is, if an input x of length n is given to T, then big O of n to the k moves of the head are enough for T to decide whether x is in L or x is not in L. If a language L is in P, we often say that membership in L can be tested in polynomial time. The reader might think that we are too imprecise here, since P does not discriminate between languages that can be accepted in big O of n time or in big O of n to the 20 time. We have two answers to that, the first one of which will be clearer after the next example. Example 18.3. Let L be the language consisting of all simple graphs that contain a triangle. Then L is in P. Solution: a Turing machine can simply go through all n choose 3 triples of the n element vertex set of the input graph and check whether all 3 pairs of vertices in any given pair are adjacent. There are only n choose 3 equals to big O of n to the cube triples to check, and in each of them there are only 3 edges to check. Finally, the head of the Turing machine never needs to travel more than n square cells between checking 2 edges, so the statement follows. Note that it paid off that in the definition of P, we did not specify what k had to be. This, for instance, obviates the question of what the size of the input should really be, the number of vertices of the graph, and or number of entries of the adjacency matrix of the graph n squared. The adjacency matrix is needed to describe which vertices are connected by an edge. There is also no need to figure out clever ways to send the head from one tape to another, since even sending it from one end to the other will not hurt. Example 18.4. Let L be the language consisting of permutations P given in the one-line notation, for which P squared is the identity permutation. Then L is in P. In this example, the size of the input is clearly the length n of P. Solution: let P equals to P1, P2, P3 until Pn for each I in n braces. If Pi is equals to j, check whether Pj is equals to I. If this always holds, accept, otherwise reject. There are n equalities to check, and between checking 2 entries, the head never needs to travel more than n cells, so there will be no more than big O of n squared steps. The class P of problems is an example of a complexity class. That is a class of problems that are roughly equally difficult to solve. While the reader might object by saying that there is quite some difference between a problem that takes n steps to solve and a problem that takes n to the 100 steps to solve, this difference is still much smaller than the difference between the latter and a problem that takes 2 to the n steps to compute. Indeed, if we have a computer that can solve a problem with input size m in log m time, then the first two problems will take log n and 100 times log n time for this computer to solve, respectively. These times will only differ by a constant factor. The last problem will take n times log 2 time, which is an order of magnitude higher. More precisely, as n goes to infinity, the first two problems will take a negligible amount of time to compute when compared to the last problem. This is our second answer to the question as to why it makes sense to put problems solvable in big O of n time and in big O of n to the 20 time into the same class. Loosely speaking, P is the set of languages that can be decided by an effective algorithm. Indeed, polynomial time is in some sense the best that we can expect, since it takes n steps just to read the input.